In this video, we are going to discuss about the unit impulse signal. The unit impulse signal is always denoted by del of t and is defined using the following equation. So del of t, as it is shown that it is always equals to 0 when t is not equals to 0. What is t? T is the x-axis continuous time, and del of t is the signal, so that is the amplitude. Usually if it is a unit impulse signal, then the amplitude is always equals to 1. So when t is not equals to 0, as it is seen in this waveform, when t is not equals to 0, either negative or positive, the value of the signal is always equals to 0. But when t is equals to 0, as it is shown, when t is equals to 0, the value of the signal is always equals to 1. But if we discuss about the discrete time function, so then you can write the same function using these equations. Del of n, like you can replace t with n and the small braces with the square brackets, is equals to 1 when n is 0. Like this value of the sample is always equals to 1 when n is equals to 0, but it is always equals to 0 when n is not equals to 0. Like for all the positive values greater than 0 or the less than 0, you can see the value of the sample is always equals to 0. Physical meaning, you can represent the same signal by having a physical meaning, which shows that it represents an instantaneous pulse, modal shock, sudden force, or momentary inputs. Idealized signal not physically realizable. And what about the graph? If you say it is a unit impulse signal, so it means that when t is equals to 0, so you have an arrow, means that you have the area or you have the amplitude is equals to 1. So arrow height represents area, so which is equals to 1. And you know that the area of unit impulse signal is always equals to 1. So we have many important properties of impulse function. The very first property is the integration. Like if you take the integral of the impulse signal, you know that the integral is always taken by a certain variable, like here it is a time dependent. So but you know that the function unit impulse is always equals to 1 when t is equals to 0. So it means that whether you are taking integral from minus infinity to infinity, so you don't need to take the integral. You can directly write that the del of t when t is equals to 0, because you know every other point the value is equals to 0. So it only has a 1 when t is equals to 0. So you can straightly write that del of t at t is equals to 0 is equals to 1. So the integral of del of t is equals to 1. The second property is the del of n is equals to u of n minus u of n minus 1. So we can prove that by having a different waveforms. So for example, so you have a unit step function for different values of n, and the waveform you can write that like starting from 0, the amplitude of all the samples is equals to 1 if the value of n is bigger than 1, bigger than 1 or bigger than 0 or equals to 0. Like 0 it's 1, 1 it's 1, 2 1, 3 1, and so on. And what about the shifted version of the unit step signal, like u of n minus 1? So it means that it is a shifted version. So whatever the samples value are, you are just shifting at place 1. So you are shifted that signal. So starting from 1, the impulse value 1, 2, 1, 3, 1, and then so on. So if you subtract these, So you can see that 1 is cancelled with 1, 2 cancelled with 2, 3 cancelled with 3, and the remaining you have only the sample value at 0 is equals to 1, so which is the unit impulse signal. So that is why this property proves that del of n is equals to u of n minus u of n minus 1. So what about the second property? If a function is multiplied by an impulse signal, then you can write that the function at t is at 0, at t is equals to 0 or t is equals to 0. Like f of t multiplied by del of t is equals to f of t is equals to 0 or f of 0. We can prove that as well. So suppose we have a function, f of t, a cosine function. So starting from that particular point at 0, so you may have an amplitude 5, and that is the cosine wave, so that is time axis. And similarly you have a unit impulse signal. So you know that the unit impulse signal is always equals to 1 at t is equals to 0. So if you multiply these two signals, like if you multiply the cosine signal with the unit impulse signal, you can see that 1 multiplied by the amplitude 5, the answer is 5. But for all the remaining values, you can see that it is 0. So del of t is 0 everywhere else, but this function has different values at different points. But if you multiply them with 0, the answer is 0. So that is why if you multiply both of them, you can write 5 amplitude at t is equals to 0. So that is equals to f of 0. So the third property is del of t minus t naught multiplied by ft is equals to f of t naught. Like if you multiply the shifted version of unit impulse signal with any function, then that will be equals to the value of the function at that particular shift. So we can prove that as well. So let's suppose, so you have same function, so f of t, so you have same function, but you have del of t minus t naught, that is a shifted version. So shifted version of that signal, so shift is at t naught. So at t naught you have this particular point, and you can, if you multiply that with this value, so maybe the value of ft at this particular point is 2. So only you will end up with that particular value, but everywhere else you can see it, the answer is 0. So t naught you have the amplitude 2, so that is why you only have the value of the function at t is equals to t naught. So that is also proved. So you have another property, that is the time scaling property. So you can write that time scaling property, that if you are multiplying 1 over k multiplied by the unit step function, the last property is very important property. So del of minus t is equals to del of t. So it shows that the unit impulse signal is an even signal. So this is very important. Like if someone is asking you what is the reflected version of impulse signal, you can straightforward say that the same, that the del of t. So because it is an even function. So I hope that you understand this unit impulse signal. So if you